spring of 1940, as the formidable Nazi panzer divisions advanced relentlessly across the French countryside, and the German Luftwaffe asserted its aerial dominance over European skies. A highly skilled engineer, Edgar Schmood, then aged 45, found himself immersed in a profound creative endeavor. Within the confines of a modest office at North American Aviation, situated in Inglewood, California, he diligently applied himself to drafting the preliminary designs for what was destined to become the most pivotal fighter aircraft of the Second World War. Yet, the narrative takes an intriguing turn. He embarked on this ambitious project entirely of his own volition, without any external commission or directive. The United States Army Air Corps had not extended any formal contract for a new fighter plane, nor had they even subtly indicated a desire for such a development. Schmood's undertaking was a calculated gamble, rooted in his professional intuition and foresight. Should his vision fail to materialize successfully, his company would inevitably bear the substantial burden of the development expenditures, and he, in all likelihood, would face the daunting prospect of seeking alternative employment. Edgar Schmood's life story unfolds, with a dramatic flair reminiscent of a captivating Hollywood screenplay, yet every detail is firmly grounded in reality. Born in Hagen, Germany, in 1899, he spent his formative years observing the groundbreaking aerial demonstrations conducted by the pioneering Wright brothers across Europe, an experience that ignited within him an enduring passion for aviation. Following the conclusion of the First World War, his professional journey led him to Fokker in Holland, a name synonymous with aeronautical innovation, being the very company responsible for constructing the iconic triplane flown by the legendary Red Baron. When the economic devastation of the Great Depression swept across the globe, he made the momentous decision to immigrate to America in 1930, arriving with little more than his meticulously crafted engineering drawings and an unyielding ambition. By 1936, his talents had secured him a position at North American Aviation, an agile and burgeoning Californian enterprise primarily known for manufacturing training aircraft. At that time, they were not yet in the same league as established giants like Lockheed or Boeing. They were, in essence, the quintessential underdogs of the aerospace industry. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Please write a comment about where you are from and what you think about the video topic. In April 1940, a pivotal moment arrived when the British Purchasing Commission approached North American's facilities with an urgent and critical appeal. Great Britain was experiencing an alarming depletion of its aerial fleet, losing aircraft at a rate far exceeding their factories' capacity for replacement. The need for combat-ready fighters, and in substantial quantities, was immediate and dire. Their request to North American was straightforward: to manufacture Curtiss P-40 Warhawks under license, a standard operational procedure that promised secure financial returns. However, company president James Dutch Kindleberger and Edgar Schmood perceived this situation not merely as a routine contract, but as an unparalleled opportunity to achieve a monumental leap forward, surpassing all existing competitors in aircraft design. Schmood boldly declared to the British representatives, with an audacity that bordered on the unbelievable, "We can design you a superior fighter from scratch within 120 days." The British found his assertion utterly preposterous, and even his own colleagues regarded him as irrational. The conventional wisdom dictated that designing a combat-ready aircraft in a mere 4 months was an impossibility. Such a feat typically demanded years of rigorous testing, extensive wind tunnel experimentation, and the inevitable failures of multiple prototypes. Yet, Schmood's confidence was not unfounded. He had, in fact, been clandestinely developing advanced fighter concepts for many months, consumed by an obsessive focus on a single, pervasive issue that plagued nearly every fighter aircraft of that era: operational range. The iconic Spitfire, for instance, was an absolute marvel in aerial dogfights, exhibiting unparalleled agility and responsiveness, but its operational endurance was severely limited, often running out of fuel after traversing only 400 miles. Conversely, the P-40 possessed a respectable range, but it suffered from an inadequate rate of climb, rendering it less effective in high-altitude engagements. German Bf-109s were undeniably lethal interceptors, but their combat radius was severely restricted by their diminutive fuel tanks, essentially tethering them to their airfields. Every air force globally confronted this brutal and seemingly inescapable trade-off. One could construct either a supremely nimble fighter or a long-range fighter, but the laws of physics, it was widely believed, precluded the possibility of combining both attributes in a single airframe. Schmood, however, held a profound conviction that these physical limitations could be artfully circumvented through a revolutionary wing design. Driven by desperation and rapidly dwindling options, the British ultimately signed the contract on May 29, 1940, stipulating a seemingly impossible deadline. The first prototype was to be delivered in just 120 days. Undeterred by the enormity of the task, Schmood swiftly assembled a dedicated team comprising 150 engineers and draftsmen, who then embarked on an arduous schedule of 24-hour shifts, operating in meticulously coordinated rotating crews. His crucial advantage, however, extended beyond mere caffeine-fueled perseverance and unwavering determination. It lay in the invaluable data provided by NACA, the National Advisory Committee for Aeronautics. This esteemed organization had been conducting extensive research and testing on a radically innovative wing shape known as a laminar flow airfoil. Schmood was now prepared to stake his entire professional career on the premise that this groundbreaking design would prove effective, not merely within the controlled environment of a wind tunnel, but crucially, in the unforgiving crucible of combat, flying at speeds exceeding 400 miles per hour, all while under hostile fire. On October 26, 1940, a mere 178 days after the momentous signing of the British contract, the distinguished test pilot Vance Breeze expertly lifted the inaugural NA-73X prototype from the runway at Mines Field in Los Angeles. The aircraft evinced an immediate sensation of lightness, responsiveness, and an almost palpable eagerness to perform. Breeze meticulously guided it through a series of dynamic maneuvers, executing precise rolls and rapid climbs, and upon landing, he delivered the ultimate commendation that engineers universally dream of hearing. "This thing handles like a sports car." Within a matter of weeks, the British bestowed upon it the evocative name, Mustang, and the initial reports appeared to resoundingly validate Schmood's audacious and seemingly impossible wager. The aircraft demonstrated exceptional speed, achieving 390 miles per hour in level flight, a velocity that surpassed nearly every other plane in the sky at that time. It exhibited remarkable smoothness in operation and maintained impressive stability. However, when pilots subsequently took the Mustang to combat altitudes, a critical flaw became glaringly apparent, and the aircraft's initial promise seemed to unravel completely. The inherent problem manifested itself with brutal clarity in early 1942, precisely when squadrons of the Royal Air Force began to integrate their newly acquired Mustangs into active service. Below an altitude of 15,000 feet, the aircraft performed magnificently, proving itself to be an outstanding platform. RAF pilots effectively deployed them for critical ground attack and reconnaissance missions, employing them to strafe German supply columns traversing France with devastating precision and efficacy. However, The moment the aircraft ascended above 15,000 feet, the Mustang underwent a dramatic and disheartening transformation, shifting from a thoroughbred warhorse to a struggling, lumbering cart horse. The engine began to wheeze audibly, its power output noticeably diminished, and its acceleration capabilities plummeted. In a high-altitude dogfight against formidable adversaries, like the Messerschmitt Bf 109 or the Focke-Wulf FW-190, the Mustang became tragically vulnerable, essentially a sitting duck for enemy fighters. Pilots, in their frustration, began to derisively refer to it as a low-altitude sports car, trapped in a high-altitude war. The primary culprit behind this critical deficiency was identified as the Allison V1710 engine, an exquisitely engineered piece of American machinery that, despite its many virtues, possessed one fatal flaw: it utilized a single-stage, single-speed supercharger. To elaborate on this without delving into an overly technical engineering discourse, it is crucial to understand that in high altitudes, the atmospheric air becomes significantly thinner. This reduction in air density means there is substantially less oxygen available for the engine to combust efficiently. A supercharger functions essentially as an air compressor, designed to force a greater volume of oxygen into the engine's cylinders, thereby maintaining power. The Allison supercharger performed admirably at sea level and at medium altitudes, consistently delivering a respectable 1,150 horsepower. However, above 15,000 feet, the altitude at which the majority of European aerial combat engagements occurred, that particular supercharger proved incapable of compressing a sufficient quantity of air. Consequently, the engine's power output drastically dropped to approximately 900 horsepower. In stark contrast, German fighters, equipped with far more sophisticated two-stage superchargers, were able to maintain their full power output up to an altitude of 25,000 feet. In the dynamic and perilous environment of a dogfight, horsepower directly translates into tactical options. It dictates speed, climb rate, and crucially, the ability to either evade an adversary or relentlessly pursue one. The Mustang, despite its beautifully optimized aerodynamics, simply lacked the necessary muscularity to leverage these advantages where it mattered most. American pilots, unfortunately, made this grim discovery through first-hand, often brutal, experience. The U.S. Army Air Forces initially relegated their P-51s to low-level reconnaissance missions, essentially assigning them the same circumscribed role that the RAF had reluctantly adopted. These photo reconnaissance Mustangs would hurtle across enemy territory at treetop level, relying on their exceptional speed and the element of surprise to avoid direct engagement with enemy fighters, rather than confronting them. This was a profoundly humiliating fate for an aircraft that had initially shown such immense promise and potential. Engineers at Wright Field in Ohio conducted countless tests, meticulously tweaking fuel mixtures and adjusting supercharger gearing in an earnest attempt to rectify the issue. However, it became painfully clear that one cannot extract performance that simply does not exist. The Allison engine, fundamentally, was not designed for the rigors of high-altitude combat. North American aviation's brilliantly conceived airframe was, regrettably, being stifled by an underpowered and inadequate heart. By the middle of 1942, the entire Mustang program began to look like an immensely costly error. The Army had placed orders for thousands of these aircraft, but the fundamental question remained: what tangible good was a fighter that proved incapable of fighting effectively at the critical altitudes where bomber formations operated? The venerable B-17 flying fortresses were enduring catastrophic losses over Germany, with dozens of aircraft being shot down per mission. This tragic toll was primarily due to the fact that their fighter escorts, predominantly P-47 Thunderbolts and P-38 Lightnings were compelled to abandon their charges and turn back before reaching the deep targets within enemy territory. The bombers would then continue their perilous journey alone, becoming easy prey for the predatory Luftwaffe fighters, which would descend upon them with the ferocity of wolves attacking sheep. It was universally understood that the ultimate solution lay in the development of a long-range, high-altitude escort fighter. The Mustang undeniably possessed the requisite range. It also boasted an exceptional airframe. However, it absolutely and unequivocally lacked the necessary altitude performance. Schmood's initially impossible design now appeared to be succumbing to a slow, agonizing death by oxygen starvation. The crucial solution, surprisingly, emerged from an unexpected quarter, a British test pilot named Ronald Harker. By chance, Harker happened to be visiting North American Aviation's Inglewood factory in April 1942. Harker, a seasoned pilot, regularly flew Spitfires for Rolls-Royce, where his duties involved testing various engines and evaluating performance modifications. When he took the controls of a Mustang cockpit for a demonstration flight, he immediately recognized a critical deficiency that American engineers had, for some inexplicable reason, overlooked. He concluded that while the airframe was extraordinary, surpassing anything he had previously flown, it was unequivocally gasping for adequate air at higher altitudes. The moment he landed, Harker dispatched an urgent telegram to Rolls-Royce headquarters in Derby, England. This message, consisting of just 5 words, would ultimately alter the course of the war. Flight testing Mustang needs Merlin engine. The Rolls-Royce Merlin was not merely another engine. It was the legendary power plant that had propelled both the Spitfires and the Lancaster bombers to their iconic status. More significantly, it incorporated a sophisticated 2-stage, 2-speed supercharger system, meticulously engineered to maintain optimal power output up to an impressive altitude of 30,000 feet. The underlying engineering of this system was remarkably complex. The first supercharger stage was responsible for compressing the incoming air. An intercooler then reduced the temperature of this compressed air to significantly increase its density. Subsequently, the second stage further compressed the air before it was forcefully inducted into the engine cylinders. This intricate setup yielded an astonishing 1,520 horsepower at 20,000 feet, nearly double the power that the Allison engine could muster at the same altitude. However, the process of swapping engines is far from a simple task, akin to merely changing a car battery. The Merlin engine was considerably heavier than the Allison, required an entirely different mounting configuration, and necessitated a complete redesign of the engine mounts, cooling systems, and propeller configurations. Rolls-Royce, recognizing the urgency and potential, did not wait for formal American approval. By October 1942, they had procured a Mustang from RAF inventory and, at their Hucknall facility, meticulously shoehorned a Merlin 61 engine into its airframe. The inaugural test flight of this modified aircraft occurred on October 13, 1942, with Rolls-Royce test pilot Captain Ronnie Shepard at the controls. Shepard ascended to 20,000 feet, fully anticipating the familiar sluggish response that had plagued earlier Mustangs. Instead, the aircraft surged forward with an exhilarating vigor, as if it had been suddenly unshackled. He then pushed it higher, to 25,000 feet, observing that it continued to climb robustly. Even at 30,000 feet, the engine maintained its powerful thrust. When he initiated a dive back down and opened the throttle fully, the airspeed indicator astonishingly touched 433 miles per hour. Shepard landed and immediately filed a report, employing words such as phenomenal and revolutionary to describe his experience. The British, recognizing the profound significance of this breakthrough, promptly designated it the Mustang X and accorded it the highest possible priority. The Mustang X project was immediately designated a paramount undertaking. Across the Atlantic, American aviation authorities, specifically North American Aviation and the Army Air Forces, were fervently striving to bridge a perceived performance gap. Whispers concerning the impressive British Merlin engine trials had been circulating, and in November 1942, Wright Field received comprehensive performance data that initially struck many as almost implausible. These astounding figures detailed a substantial 50 miles per hour surge in top speed and a remarkable elevation in service ceiling, escalating from 31,000 feet to an extraordinary 41,900 feet. Understandably, a segment of the engineering community harbored suspicions of potential measurement inaccuracies, given the sheer magnitude of the reported enhancements. However, skepticism soon gave way to undeniable reality when the inaugural American-built Merlin-powered Mustang, officially designated the XP-51B, soared into the skies from Inglewood on November 30, 1942. Test pilot Bob Chilton, after expertly putting the aircraft through its rigorous paces, transmitted an eagerly enthusiastic report, his voice barely concealing his elation. "This thing climbs like a homesick angel," he declared, instantly recognizing the profound superiority of the new variant. The metamorphosis of the airframe was nothing short of absolute. The very same Mustang airframe that had previously demonstrated considerable limitations above 15,000 feet now asserted unchallenged dominance at altitudes of 25,000 feet, and proved exceptionally capable in aerial combat even at 35,000 feet. Concurrent with these developments, the Packard Motor Company, situated in Detroit, commenced the licensed manufacturing of the Merlin engines, producing them under the designation Packard V1650. This power plant was, in essence, an American rendition of the Merlin, thoughtfully adapted with modified tooling to facilitate efficient mass production, thereby ensuring a steady supply for the burgeoning demand. By the dawn of 1943, a steady stream of P-51B Mustangs, now equipped with their potent Merlin engines, was rolling off the busy assembly lines not only at the original Inglewood facility but also from a newly established factory in Dallas, Texas, significantly accelerating production. In contrast, the earlier Allison engine Mustangs were quietly, yet efficiently, repurposed for alternative duties, primarily reassigned to critical roles in ground attack and aerial reconnaissance, where their capabilities remained valuable. The true, definitive Mustang, the formidable fighter destined to provide crucial long-range escort for heavy bombers on perilous missions deep into enemy territory, such as those to Berlin and back, had finally materialized. Edgar Schmood's ingeniously designed airframe had at last discovered its quintessential power plant, and the German Luftwaffe was on the precipice of a stark revelation regarding the devastating potential of 1,500 horsepower, coupled with revolutionary laminar flow wings, when wielded by supremely skilled and resolute pilots. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. In the comments below, let us know where you are watching from and what your thoughts are on the incredible transformation of the P-51 Mustang and its pivotal role in aviation history. Let us now delve into the actual engineering brilliance that rendered Schmood's design truly groundbreaking: the wing itself. This particular aspect often causes many to lose interest as engineers begin to articulate highly specialized terminology, such as boundary layer and Reynolds numbers. However, we urge you to persist, as comprehending this fundamental innovation is precisely what differentiates a merely competent fighter aircraft from an unequivocally legendary one. Inherent to the flight of every aircraft, the wing inevitably pulls air molecules along its surface, creating a dynamic interaction. Typically, this interaction results in what is known as turbulent airflow. One might visualize this phenomenon as countless minuscule whirlpools and chaotic eddies swirling unpredictably across the wing's surface. Turbulent air fundamentally equates to increased drag, and this drag, in turn, necessitates the expenditure of precious fuel simply to overcome the resistance of the air itself. Schmood's primary objective, therefore, was to mitigate or, ideally, eliminate as much of this detrimental turbulence as technologically feasible. This critical challenge was met with the introduction of the NACA 45-100 series laminar flow airfoil, a pioneering design meticulously developed by the brilliant engineer Eastman Jacobs at the Langley Research Center in Virginia during the latter half of the 1930s. Jacobs had dedicated numerous years to exhaustive research within wind tunnels, intently studying the intricate ways in which air traversed wing surfaces. His tireless efforts led to a profoundly counterintuitive discovery. While most aircraft wings of the 1930s typically featured their thickest point positioned approximately 25 to 30% back from the leading edge, Jacobs boldly repositioned this point of maximum thickness much further aft, to 45%, effectively almost halfway along the wing chord. This seemingly subtle, yet profoundly impactful, alteration generated a distinct pressure gradient that proved instrumental in preserving smooth, laminar airflow, meaning the air molecules flowed in highly organized, parallel layers rather than in chaotic, turbulent patterns, across a significantly extended portion of the wing's surface. The empirical data derived from this innovation were truly astonishing. Extensive wind tunnel tests conclusively demonstrated that laminar flow wings possess the capability to reduce aerodynamic drag by a remarkable 30 to 40% when compared to conventional airfoils operating at typical cruise speeds. Such a substantial reduction in drag, specifically 30% less, offered profound operational advantages. Aircraft could either traverse the same considerable distances using significantly less fuel or, alternatively, carry a larger volume of fuel to achieve dramatically greater ranges. However, and this aspect was absolutely critical, the efficacy of laminar flow was entirely contingent upon the wing surface being impeccably smooth. We are referring to imperfections so minute they were measured in mere thousandths of an inch. Even a single protruding rivet head, the residue of an insect strike, or an uneven application of paint possessed the potential to disrupt the delicate laminar airflow, causing it to abruptly transition to turbulent flow and, consequently, completely negate the profound aerodynamic advantage. A considerable number of engineers at the time largely deemed it an insurmountable challenge to uphold such exacting precision in the context of mass production, let alone to maintain it under the brutal realities of combat conditions, where aircraft frequently sustained bullet holes and underwent rudimentary battlefield repairs. Nevertheless, Schmood demonstrated an almost obsessive dedication to manufacturing tolerances, which were widely considered wildly impractical, even insane, for the industrial standards of 1940. In response to this demanding requirement, North American aviation pioneered advanced flush riveting techniques, meticulously ensuring that rivet heads sat perfectly level with the wing skin, rather than creating any protuberance. They additionally employed sophisticated jigs and fixtures that secured wing panels to remarkably tight tolerances of plus or minus 0.05 inches. Furthermore, skilled workers painstakingly hand-sanded wing surfaces and meticulously applied multiple coats of primer and paint, wet sanding between each successive layer until the surface achieved a flawless, glass-like smoothness. The rigorous quality inspectors were known to reject entire wings that, by the less stringent standards of other manufacturers, would have been considered entirely acceptable, underscoring the uncompromising commitment to perfection. While these extraordinarily meticulous production methods undoubtedly augmented both the time and monetary investment required for each aircraft, the resulting performance unequivocally validated these expenditures. The P-51's internal fuel capacity initially stood at 269 gallons, a figure that was later expanded to an impressive 489 gallons with the strategic addition of external drop tanks. This substantial fuel load translated directly into an unparalleled effective combat radius of 750 miles, signifying that the Mustang possessed the capability to fly 750 miles, engage in aerial combat for a full 20 minutes, and still successfully return to its base. To contextualize this achievement, one need only compare it to contemporary fighters. A Spitfire Mk-9, for instance, carried merely 85 gallons of internal fuel, affording it a combat radius of barely 400 miles, while a P-47 Thunderbolt, with its 305-gallon capacity, managed a combat radius of 475 miles. The Mustang, therefore, was not simply a marginally superior aircraft. It fundamentally established an entirely new class of long-range fighter performance. And herein lay a particularly elegant aspect of its design. Owing to the exceptional efficiency of the laminar flow wing at cruise speeds, the Mustang paradoxically achieved greater distances by actually flying faster. When cruising at an optimal speed of 280 miles per hour, the aircraft consumed fuel with such remarkable efficiency that the strategic addition of external tanks effectively transformed it into a weapon of profound strategic consequence. Bomber crews, who had long endured the harrowing experience of being abandoned by their escorts deep within enemy territory, began affectionately referring to the Mustangs as "little friends." This moniker reflected a profound shift. For the very first time in the relentless air war over Europe, these "little friends" possessed the endurance to remain with them throughout the entirety of their perilous missions, from the initial rendezvous all the way to the target and, crucially, back to the safety of home. The date was March 4, 1944. 64 P-51B Mustangs, proudly bearing the insignia of the 4th Fighter Group, gracefully lifted off from Debden Airfield in England at precisely 10:15 in the morning. Their wings, visibly heavy, were laden with 110-gallon drop tanks, essential for the arduous journey ahead. The mission briefing had been delivered with stark clarity and without embellishment. "Escort the B-17 bombers to Berlin and bring them home." Berlin, the very capital of Hitler's Third Reich, represented a 1,000-mile round trip deep into the heart of enemy territory, a destination where no Allied fighter had ever before dared to venture. The bomber crews, accustomed to the limitations of previous escorts, struggled to fully believe the audacious promise. They had, after all, witnessed too many escort fighters reluctantly waggle their wings in a gesture of apology and then peel away at the German border, their dwindling fuel gauges compelling them to return, leaving the vulnerable bombers exposed to the predatory advances of Luftwaffe fighters. However, this particular mission was destined to unfold differently. Lieutenant Colonel Don Blakesley, a seasoned combat veteran whose distinguished service included flying Spitfires with the Royal Air Force before his transfer to American squadrons, commanded the formidable formation. Blakesley possessed a profound understanding of the mission's immense strategic implications. His reasoning was clear. If Mustangs could successfully reach and operate over Berlin, the Luftwaffe would effectively be stripped of any remaining sanctuary. German fighter units had, by this point, strategically retreated deeper into Reich territory, operating from bases they erroneously considered impervious to American fighter escorts. Berlin, both psychologically and practically, embodied the very heart of the German air defense system. The ability to engage in combat over Berlin signaled the capacity to fight effectively anywhere within the Reich. The weather conditions were characteristic of a miserable March day. Thick, oppressive clouds blanketed the English Channel, and icing conditions prevailed at high altitudes, posing a significant challenge. Several Mustangs were compelled to abort their mission due to various mechanical malfunctions, yet the resolute main formation pressed onward undeterred. They penetrated German airspace at a cruising altitude of 27,000 feet, their throttles carefully set to an efficient cruise speed, meticulously conserving every precious gallon of fuel. The vast bomber stream, comprising 316 B-17s, stretched for miles across the sky, relentlessly advancing towards their primary objective, a crucial ball-bearing factory situated in Erkner, just outside Berlin. At approximately 11:40, near the city of Brunswick, the first Luftwaffe fighters emerged from the clouds, a menacing mix of Messerschmitt Bf 109GS and Focke-Wulf FW 190 as, diving aggressively from above. Under normal circumstances, at this advanced point in the mission, the Allied escorts would have long since departed, forced home by fuel constraints. Yet, on this day, the Mustangs remained, their unexpected presence causing a palpable moment of hesitation among the German pilots. Years of ingrained operational experience and tactical doctrine had unequivocally taught the German pilots that American fighters simply should not, and could not, penetrate this far east into Reich territory. That crucial, fleeting moment of hesitation, born of disbelief, ultimately proved to be their undoing. The Mustangs, without delay, broke formation and vigorously engaged the enemy, skillfully turning inside the German fighters and exploiting their superior speed at altitude to dictate the terms of engagement. Captain Don Gentile, a formidable ace, swiftly shot down two Bf 109s within a mere 3 minutes, expertly leveraging the Mustang's exceptional climb rate to gain advantageous positions above his adversaries, from which he executed devastating gravity-assisted dives. The revolutionary laminar flow wings, over which Edgar Schmood had so obsessively labored, enabled the Mustang to maintain precise control at velocities where other contemporary fighters would invariably begin to buffet and shake uncontrollably. German pilots found themselves in the unprecedented and deeply unsettling position of being simultaneously outrun and outclimbed, a tactical nightmare they had never before encountered. The ensuing furball, the pilots' vivid slang for a chaotic, tangled aerial dogfight, sprawled across an astonishing 50 miles of German sky. Yet, amidst the swirling chaos, one critical fact remained steadfast. The B-17 bombers continued their unwavering trajectory towards Berlin, shielded and protected by their vigilant Mustang escorts. At 12:15, the massive formation finally crossed into Berlin's tightly defended airspace. Immediately, the formidable flak batteries erupted, filling the sky with ominous black bursts of exploding shells. However, the prevailing weather conditions, which had initially posed challenges, now ironically worked in the Allies' favor. The cloud cover was so dense and pervasive that the anti-aircraft gunners below were effectively firing blind, unable to accurately track their targets. Consequently, the B-17s successfully released their bomb loads through the thick overcast, utilizing sophisticated radar guidance, and then promptly turned for home. The Mustang pilots, with a sense of relief, checked their fuel gauges. They had, as anticipated, expended the contents of their external drop tanks and were now operating on internal fuel, but the meticulous calculations still held true. The return journey remained entirely feasible. The homeward leg would be flown at an optimal cruise speed, with strict instructions for no unnecessary maneuvering, maintaining straight and direct lines back to base. By 1430, the entire formation had safely returned over the North Sea, and by 1500 hours, their wheels were gently touching down on the welcoming runways of English airfields, having completed a mission that redefined the boundaries of aerial warfare. The mission's stark statistics eloquently narrated the story of its success and sacrifice. 5 bombers were regrettably lost, predominantly to the fierce anti-aircraft fire. The Luftwaffe, in its official reports, erroneously claimed the destruction of 11 Mustangs. However, the actual losses amounted to 5 aircraft, with 3 of those pilots fortunately rescued. American fighters, in turn, reported the verified destruction of 13 German aircraft during the engagement. However, the true, enduring victory transcended mere kill ratios and numerical tallies. Its profound significance lay in the immense psychological impact it delivered. Luftwaffe pilots, their voices laced with incredulity, radioed their controllers with disbelieving reports. American fighters over Berlin. The legendary Reichsmarschall Hermann Göring, the supreme commander of the Luftwaffe, is famously reported to have conceded, "When I saw Mustangs over Berlin, I knew the jig was up." The long-held myth of Fortress Germany, the notion of an impenetrable homeland, had irrevocably shattered at 27,000 feet, a direct consequence of Edgar Schmood's seemingly impossible yet brilliantly executed wing design. Yet, merely reaching Berlin was only one half of the complex equation. The Mustang was also inherently required to survive the fierce engagements it encountered once it arrived at such distant, heavily defended targets. And it was precisely in this critical aspect that Schmood's visionary design philosophy yielded unforeseen and deeply significant dividends that virtually no one had initially anticipated. Unforeseen advantages and remarkable outcomes. In 1944, the German aviators were far from inexperienced novices. A significant number among them were esteemed aces, boasting hundreds of hours in aerial combat, having endured the harrowing crucible of the Battle of Britain and the relentless Eastern Front. Their formidable aircraft, such as the Messerschmitt Bf 109G and the Focke-Wulf FW-190A, were meticulously engineered for high-altitude interception. The Bf 109G could achieve speeds of 400 miles per hour and ascend at an impressive rate of 3,100 feet per minute, while the FW-190A, a brutal radial engine fighter, was renowned for its exceptional resilience to damage and its unparalleled roll rate. On paper, these German marvels appeared to be perfectly matched adversaries for any Allied fighter. However, in the unforgiving reality of combat, the American P-51D Mustang transformed even the most seasoned German pilots into seemingly amateurish opponents. The P-51D, introduced in mid-1944 and featuring a distinctive bubble canopy offering 360-degree visibility, reached a maximum speed of 437 miles per hour at 25,000 feet. While certainly swift, this speed was not overwhelmingly superior to that of its German counterparts. The Mustang's true, decisive advantage lay in its extraordinary climb rate of 3,200 feet per minute. In the intense maelstrom of a dogfight, with the Merlin engine roaring at war emergency power, the pilot, who could secure the superior altitude, invariably commanded the engagement. This tactical supremacy allowed them to initiate a dive, leveraging gravity to augment their speed, dictate the terms of the attack, and disengage by climbing away if the situation deteriorated. German pilots consistently discovered that Mustangs could not only match their ascent, but also continue climbing long after their own engines began to falter, gasping for the thinner air. The two-stage Merlin supercharger was simply far more efficient at oxygenating its engine at altitudes exceeding 28,000 feet than any system the Luftwaffe could deploy. Furthermore, turn performance was a critical differentiator between good fighters and truly exceptional ones, and here, the Mustang's innovative laminar flow wing once again proved its mettle. The Mustang possessed the remarkable ability to sustain a turn radius of approximately 1,200 feet at 300 miles per hour without experiencing an undue loss of energy, enabling it to execute tight, rapid turns while preserving its speed. In contrast, the Focke-Wulf FW-190 required a wider turning arc. The Messerschmitt Bf 109, while capable of an initially tighter turn, rapidly bled off speed, leaving its pilot dangerously exposed. American pilots swiftly learned to exploit these inherent weaknesses. If a Messerschmitt managed to position itself on a Mustang's tail, the American pilot would initiate a climbing spiral turn. The 109 would inevitably follow, both aircraft enduring perhaps 4 or 5 gs, a force sufficient to induce peripheral graying of vision. Yet, the Mustang consistently maintained its energy state with greater efficacy. After just 2 complete turns, the 109 would be wallowing, slow, and critically vulnerable, whereas the Mustang still retained ample speed to reverse the engagement. Moreover, diving speed was of paramount importance when missions went awry. The Mustang was officially cleared for dives up to 505 miles per hour, although pilots frequently pushed past this limit while pursuing retreating German jets. The airframe exhibited unwavering structural integrity, devoid of wing flutter or control lockup. Edgar Schmood, the Mustang's brilliant designer, had meticulously incorporated structural strength into every component through stressed skin construction, a method where the aluminum skin itself bore aerodynamic loads, rather than relying solely on internal frameworks. German fighters, particularly the Bf 109, often suffered from elevator flutter during high-speed dives, compelling their pilots to exercise caution and rarely exceed 450 miles per hour. This critical 50 miles per hour difference meant that a diving Mustang could effortlessly intercept almost any fleeing adversary or evade nearly any pursuer. Stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The Mustang's formidable firepower decisively sealed its superiority. The P-51D was armed with 6.50 caliber Browning M2 machine guns, 3 positioned in each wing, carrying a total of 1,800 rounds. Each weapon discharged 800 rounds per minute, and at a typical convergence range of 300 yards, all 6 streams of bullets converged into a lethal cone of destruction approximately 6 feet in diameter. A mere 2-second burst would unleash roughly 160 bullets into this destructive cone, tearing through the comparatively delicate structure of German fighters. This sheer volume of fire was utterly devastating. Pilots frequently recounted witnessing wings folding, tails separating, and cockpits disintegrating under the concentrated fury of .50 caliber fire. The Mustang was not merely faster and more agile. It struck with far greater force. Even highly decorated German aces, who had survived years of brutal combat, found themselves completely outmatched by American pilots with as little as 50 hours of combat experience, simply because the Mustang furnished these relative novices with the tools to compensate for their inexperience. This, indeed, is the quintessential hallmark of truly exceptional engineering. It renders the profoundly difficult appear remarkably effortless. Let us now consider the profound ramifications when thousands of these extraordinary aircraft were deployed, flown by pilots whose primary directive was not to simply shoot down enemy fighters, but rather to ensure the safe return of the bombers. This pivotal doctrinal shift, coupled with the Mustang's unparalleled capabilities, precipitated a statistical slaughter in the skies. Between January 1944 and May 1945, P-51 Mustangs were officially credited with the destruction of an astonishing 4,950 enemy aircraft, a figure surpassing that of any other Allied fighter in the European theater. This impressive tally encompasses 4,131 aircraft shot down in fierce air combat, and an additional 819 obliterated on the ground during daring strafing runs. However, raw kill numbers alone present only a partial narrative. One must critically examine the strategic objectives these kills ultimately achieved. The 8th Air Force, which constituted the principal American bomber command stationed in England, suffered an average loss of 350 heavy bombers each month during the latter half of 1943. This translated to approximately 3,500 highly trained aircrew members either killed or captured every 30 days, a rate utterly unsustainable by any conceivable measure. Each B-17 or B-24 bomber carried a crew of 10 men, represented hundreds of thousands of dollars in manufacturing costs, and necessitated months of rigorous crew training. The Luftwaffe was, in essence, winning the attrition war by forcing unescorted bombers to navigate a deadly gauntlet of concentrated fighters at critical choke points along their routes to vital German industrial targets. In October 1943, a particularly brutal raid on Schweinfurt resulted in the loss of 60 bombers out of 291 dispatched, a staggering 20% loss rate that, had it persisted, would have irrevocably bankrupted the entire bombing campaign within a matter of months. The timely arrival of long-range P-51B escorts in December 1943 instantly and dramatically altered this grim mathematical equation. By March 1944, the bomber loss rates had plummeted to a mere 3.5% per mission. By June 1944, in the aftermath of D-Day, when Mustang groups were frequently executing multiple daily missions, this rate further declined to below 2%. The Luftwaffe did not suddenly become less proficient in aerial combat. Rather, they were forced into an untenable and impossible strategic predicament. German fighters were compelled to engage the bomber formations to prevent the catastrophic destruction of the Reich's industrial infrastructure. However, engaging these bombers now meant running a deadly gauntlet through a protective screen of Mustangs that possessed the range and capability to pursue them anywhere across the vast European skies. Luftwaffe pilots began to report increasingly frequent situations where they would visually acquire bomber formations, but found themselves unable to launch an attack because the omnipresent Mustangs maintained a decisive altitude advantage. The role of the escorts had unequivocally shifted from a purely defensive posture to an aggressive, offensive operational strategy. Ground attack missions injected yet another devastating dimension into the conflict. Once bomber formations were safely en route back to their bases, Mustang squadrons would descend to treetop level, embarking on opportunistic hunts for targets, locomotives, military trucks, vital fuel depots, and enemy aircraft conveniently parked on airfields. The very same .50 caliber guns that could effortlessly shred a fighter at high altitude proved equally effective against the thinly armored ground targets. German train engineers quickly learned to abandon their locomotives the moment they spotted approaching Mustangs, as a single, precise strafing pass could instantly transform a steam engine into a twisted mass of scrap metal. Luftwaffe airfields were forced to relocate aircraft into blast-proof revetments and disperse them across numerous satellite fields, a measure that only served to complicate and hinder maintenance and operational logistics. The Mustang effectively compelled the entire German air defense system into a perpetually reactive mode. The human and material cost, however, was far from trivial. The 8th Air Force suffered the loss of approximately 2,520 P-51s between 1943 and 1945, with roughly 1,300 pilots tragically killed. This represented a loss rate of approximately 33% relative to enemy aircraft destroyed, a favorable exchange ratio, yet undeniably painful. Many of these losses stemmed from deadly flak and intense ground fire encountered during perilous low-level strafing runs, which constituted the most dangerous mission profile. Even a single rifle bullet penetrating the radiator could fatally doom a Mustang by inducing coolant loss and subsequent engine failure. However, the strategic calculus was both brutal and unequivocally clear, trading one highly trained fighter pilot for 2 or 3 German fighters, in addition to preserving the lives of dozens of bomber crew members, was a mathematically indispensable necessity to ultimately secure victory in the war. By the spring of 1945, the formidable Luftwaffe had been systematically ground down to a mere shadow force, operating sporadically with woefully inadequate fuel reserves and manned by inexperienced, green pilots who often possessed only about 30 hours of rudimentary flight training. While the Mustang did not singularly achieve air superiority, it undeniably rendered victory inevitable and dramatically accelerated its realization by several crucial months. The war concluded in May 1945, and the vast majority of wartime aircraft designs swiftly vanished into scrapyards, or were relegated to museums within a few short years. The future, it was widely acknowledged, belonged unequivocally to jet propulsion. Everyone understood this undeniable truth. The Messerschmitt Me 262 jet fighter had already conclusively demonstrated the obsolescence of piston engines, even if its belated arrival precluded it from saving Germany. Yet, Edgar Schmood's magnificent Mustang steadfastly refused to retire gracefully into obscurity. The fundamental design principles ingeniously embedded within its laminar flow wing and robust stress-skin fuselage continued to find novel applications long after the final combat mission had been flown over the ravaged landscapes of Europe. The subsequent narrative of what transpired next unveils a profound truth about truly revolutionary engineering. A truly great design possesses the inherent capacity to transcend its original, intended purpose. When the Korean War erupted in June 1950, the newly independent United States Air Force suddenly found itself in urgent need of reliable ground attack aircraft capable of operating effectively from rudimentary forward air strips and resilient enough to withstand intense anti-aircraft fire. The early jet aircraft of that era were notoriously temperamental, voraciously fuel-hungry, and necessitated extensive concrete runways for their operations. Consequently, the F-51D Mustang, which had been redesignated when the Air Force gained its independence in 1947, was swiftly brought out of mothballs and deployed to the Korean peninsula within a matter of weeks. Pilots discovered that the aircraft performed ground attack missions with exceptional prowess, capably carrying bombs, rockets, and napalm while simultaneously absorbing battle damage that would have irrevocably brought down a jet fighter. The Mustang's incredibly reliable Merlin engine and its robust airframe meant that it could operate with remarkable efficiency from primitive airfields situated perilously close to the front lines. These venerable aircraft ultimately flew an astonishing 62,607 combat sorties in Korea, losing 351 aircraft primarily to devastating ground fire. This was a truly remarkable performance for a design that was already a decade old, underscoring its enduring adaptability and timeless engineering brilliance. Already a full decade in service. However, the most astonishing demonstration of enduring utility emerged within the realm of foreign military applications. Numerous smaller nations, often operating with constrained fiscal resources, simply could not bear the exorbitant costs associated with acquiring advanced jet fighters or establishing the extensive logistical infrastructure required for their continuous maintenance. In stark contrast, these very same countries found the Mustang to be an exceptionally practical and cost-effective solution, capable of sustained operations with remarkably minimal logistical overhead. A prime example is the Israeli Air Force, which famously deployed P-51D aircraft with considerable success during the pivotal 1948 Arab-Israeli War and commendably retained them in active duty until 1961. Even more remarkably, the Dominican Air Force continued to operate its fleet of Mustangs until an incredible 1984. Yes, the year 1984, a staggering 44 years after the inaugural flight of its prototype. It is crucial to understand that these venerable aircraft were not merely static museum exhibits or performers in nostalgic air show demonstrations. They were fully operational combat platforms, diligently conducting vital border patrol missions and engaging in demanding counterinsurgency operations. The sheer fact that air forces in developing nations, often contending with limited access to specialized parts and technical expertise, managed to meticulously maintain the intricate Merlin engines of these aircraft, stands as a profound testament to the exceptional engineering and robust design of the entire Mustang package. Edgar Schmood himself, the visionary behind the Mustang, progressively transitioned to a diverse array of other groundbreaking projects. Following the conclusion of the war, he seamlessly integrated into North American aviation's nascent jet programs, ultimately ascending to the prestigious position of chief designer for the iconic F-86 Sabre. This revolutionary swept-wing fighter subsequently achieved unparalleled aerial supremacy, decisively dominating the Soviet-designed MiG-15s during the intense dogfights over the Korean peninsula. A discerning examination of the F-80SIX's fundamental design philosophy reveals unmistakable traces of its Mustang lineage, a pronounced emphasis on maximizing pilot visibility, the meticulous pursuit of highly efficient aerodynamics, and an unwavering commitment to achieving an impressive operational range. While the Sabre was unequivocally not merely a Mustang retrofitted with a jet engine, it undeniably inherited the same meticulous, almost obsessive, attention to the critical aspects of drag reduction and structural efficiency that characterized its propeller-driven predecessor. Schmood ultimately retired from his illustrious career in 1960 and passed away in 1985, having lived long enough to witness his seemingly impossible 1940 design, a triumph of engineering ingenuity, still actively flying in combat roles 4 decades after its initial conception. It is a rare privilege for any engineer to experience such a profound and enduring legacy. Please stay with us and watch the end of the video. We will be grateful for your like and subscription. Write a comment about where you are from and what you think about the video topic. The profound technical influence of the Mustang permeated far deeper than the singular impact of individual aircraft designs. The revolutionary NACA 45-100 laminar flow airfoil, a design principle upon which Schmood audaciously staked his entire professional career, eventually became the foundational bedrock for extensive research into the development of supercritical wings, which are now ubiquitously employed on contemporary commercial airliners. Aeronautical engineers, diligently studying the complexities of transonic flight during the 1960s, made a crucial realization. The established principles of laminar flow could be adeptly applied to effectively delay the undesirable formation of shock waves at high subsonic velocities. Boeing, a titan in aerospace manufacturing, skillfully integrated these invaluable lessons into the designs of its highly successful 737 and 747 aircraft families. Similarly, Airbus, another leading aerospace innovator, leveraged comparable aerodynamic concepts in the development of its popular A320 family. Consequently, every single time a passenger boards a modern commercial airliner, benefiting from its impressive long-range capabilities and exemplary fuel efficiency, they are, in essence, directly experiencing the practical application of aerodynamic principles that Edgar Schmood definitively proved could function not merely within the controlled environment of a wind tunnel, but also under the extreme duress of combat at speeds exceeding 400 miles per hour, with the added peril of incoming enemy fire. Ultimately, the P-51 Mustang served as an unequivocal validation of a fundamental truth that military procurement offices, even to this day, frequently struggle to fully grasp and accept. Occasionally, the most optimal and groundbreaking solutions emanate from an ingenious engineer whom no one specifically solicited, who tackles a complex problem through entirely unconventional methods, and who achieves these feats within a time frame that was initially dismissed as utterly impossible. Schmood's seemingly unachievable 120-day deadline in 1940 miraculously culminated in the creation of an aircraft that profoundly influenced the trajectory of aerospace design for 3 subsequent generations. This remarkable achievement transcends mere good engineering. It represents a profound vision, meticulously executed with unparalleled precision under circumstances of immense and unrelenting pressure. The Allied bombers successfully reached their targets in Berlin and subsequently returned safely to base, largely because one determined German immigrant steadfastly refused to concede that the immutable laws of physics had already predetermined the limits of what was truly possible.